Our next lesson in our unit on gas laws is going to be Gas Laws 1.1. And in this lesson, we're going to look at just two things. We're going to look at the combined gas law, and we're going to look at the ideal gas law. So to start off with the combined gas law, we have three existing gas laws that we've discussed so far. We have Boyle's law, and Boyle's law is going to be the one that is P1V1 equals P2V2. The next one that we're going to talk about is going to be Charles's law. Charles's law says V1 over T1 equals V2 over T2. And we have Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So, in Boyle's law, the pressure and the volume change, but the temperature does not. And so what we have going on here is, in this case, is the temperature is going to be a constant. In Charles' law, the volume and the temperature change, but the pressure is a constant. And in Gay-Lussac's law, the pressure and the temperature change, but the volume is a constant. And so we have something that works as long as only two things change, but one of them has to stay the same. The question is, what happens though if all three of the things change? We change the pressure and the volume and the temperature, and they all change. If that happens, you can't use Boyle's law or Charles' law and Gay-Lussac's law, but instead we could sort of take all three of these and we can merge them together into a combined gas law, because it combines these three laws. And the combined gas law is what we have down here at the bottom. P1V1 over T1 equals P2V2 over T2. And so the original pressure, P1, and we have then that times the original volume, V1, times the original, divided by the original temperature, T1, equals the final pressure, T2, times the final volume, V2, divided by the final temperature, T2. Now, in this case, the same rules as far as units apply. Pressure can be pretty much in any unit that you'd like, as long as it's a unit of pressure, and as long as P2 has the same units as P1. Volume, the same thing is true, is that we can have whatever units of volume that we like, as long as it's a unit of volume, as long as it's the same as the unit of V2, and temperature works the same way as before, in that it always has to be in Kelvin. No choices there. So it is the same on both sides, just sort of automatically. So let's take a look at how we might go about doing one of these problems. And so to do that, we're going to sort of move a little forward here. And so here's our example, is that what we know is a 15.6 liter container of gas is collected at 801 torr and 24 degrees Celsius. What is the volume of the gas if it is brought to STP? And so basically what we're going to do in this case is we first want to write out our combined gas law. Combined gas law says this: P1 times V1 over T1 is going to be equal to P2 times 2 times T2 times V2. Let me correct that right there. Get rid of that there. P2 times V2 over T2. And so to do this, let's see what we have for our original pressure. So our original pressure, 15.6 liter container of a gas is collected at 801 torr. And so original pressure is going to be 801 torr. And so this simply means that the final pressure has to be in torr, times the original volume, V1, and it says that's 15.6, and so 15.6 liters, all over the original temperature. And the temperature that's mentioned here is 24 degrees C, and so to work this out, we're going to have to convert this to Kelvin. So 24 degrees C plus 273.15, and so if you go ahead and take out the calculators there if you need them, so we get 297.15 Kelvin is what we get for this. And so on bottom, 297.15 Kelvin goes down there, and this is going to equal to P2, the second pressure. Well, it says that it's at STP, and if it's at STP, then standard temperature and pressure, and so standard pressure in torr is going to be 760. And so we get 760 torr on this side, times the volume, the volume afterwards, and we don't know that. That's what we're looking for. And so this would be just V2 right here. The unit's going to have to be in liters, because that's what it was on the left side. It's the unit we started with, divided by the temperature. Now it's STP, standard temperature. Standard temperature is 0 degrees Celsius, or 273.15 Kelvin. So this is what we have here. So we want to solve for V2. And so to solve for V2, we're basically going to do a little bit of cross multiplication. So we can do 801 torr times 15.6 liters divided by 297.15 K. But we want to take the 760 and move it on bottom, the 273.15 and move it on top and multiply those up. And that should give it to give our final answer here. And so if you once again take out the calculators here, 801 torr times 15.6 liters, and then times the 273.15, because that's being cross-multiplied up to the top, and then divided by 297.15 K, and we also divide that by 760 torr. And so when we do that, we end up with an overall V2 of 15.113 liters. Significant figure-wise is that taking a look at that, what we see here is that our original 15.6 has 3 significant figures, 24 degrees has 2 significant figures, 801 torr has 3 significant figures. And so normally we'd have 2 here, except for the fact that this one right here is round to the ones place for your temperature. And so when that comes over here, that'll be around the ones place here, which gives 3 significant figures. And so and the 273.15 is exact. So that means that we're going to have 3 significant figures for our final answer. So 1, 2, 3. And so our final volume here is going to be 15.1 liters. And so that will be our final answer here. That's how you go about using the combined gas law. Pretty much you just take what you've got, you put it into the combined gas law equation, make sure your units match up, and cross-multiply to solve. And so that's sort of how that works. So let's carry on here. And so continuing, we've got another example here. So in this case, what we know is a weather balloon is measured to have a volume of 310 liters before lifting off when the ground conditions are 102 kilopascals and 18 degrees Celsius. The balloon then rises to an altitude where the pressure is halved, and it's found at that point to have a volume of 480 liters. So what's the temperature at that altitude? So let's go ahead and set up our ideal gas, our combined gas law. So we know P1 V1 over T1 is equal to P2 V2 over T2. And so what's the original pressure of the weather balloon? Let's see, pressure of the weather balloon, it says 102 kilopascals. And so we'd say 102 kPa times the original volume of the balloon. It has a volume of 310 liters. So times 310 liters divided by the original temperature, which is 18 degrees Celsius. And so once again, 273.15 plus 18 degrees Celsius. And so doing this gives us 291.15. I'm doing the math right, Kelvin. So 291.15 kelvins. And so we've got that equals P2. And it says the balloon rises to the altitude where the pressure has halved. And so originally we had a pressure of, as we said, where was it going here? Of 102 kilopascals. Half of that would be 51. And so I know I have a pressure of 51 kPa. It says that it has a volume at this point of 480 liters. So 480 liters like this, divided by my T2, which I do not know because it asks what is the temperature at that altitude. So once again, we're going to go ahead and we're going to cross multiply this guy. In this case, what we're going to have to do is we have to get this T all by itself. So we're going to have to get the T2 up top. And so in doing that, we're going to have to move the 291 up here, and we're going to have to move these two guys down to the bottom. So that effectively what we're going to have is that to work this out, we've got on our right side our 51 kilopascals times our 480 liters. And then you're going to multiply that times the 291.15 from the bottom of the left. And then you're going to divide that by the two guys on the top on the left, which are 310, and then divide that by 102. So overall is that what we end up getting for this is that T2 is equal to, unrounded, 225.40 Kelvin. Significant figure-wise is that we have 3 significant figures for our kilopascals originally. We have two significant figures for our one that's after it's halved over here. Two significant figures on our volume in liters, two significant figures on our volume in liters over here. So we're going to have two significant figures here. And so T2 would be 230, that's a 3, kelvins. And that would be our final answer here using the combined gas law. And that is how you basically work out combined gas law problems. So moving forward as we do here, let's take a look. There is one thing that we have left out of our combined gas law, because we've talked about how, pressure can change a gas. We talked about how volume can change a gas. We talked about how temperature can change a gas. But there's one other way we can change a gas that we haven't talked about. Because let's say we've got a tire. If you want to increase the pressure in the tire, there are a couple ways you could do it. You could increase the temperature. All right. If you increase the temperature, the molecules go faster. They strike the walls of the tire at a higher speed, and so they put more force, and so you increase the pressure. You could decrease the volume. If you decrease the volume of the tire, then basically you are packing more molecules into a tighter space, and so more molecules will hit each surface area of the tire there. But you don't use either one of those whenever you need to basically increase the pressure in your tires in your car. You don't say, oh, my tire pressure is a little low. I'm going to go and drive to Mexico so I can have a higher temperature. Or you don't say, oh, I'll just squeeze my tires in tighter so then I have a higher temperature. Common sense thing here is what you do. You add air to your tires. All the cases we've done before have assumed that basically that the number of molecules or number of moles of gas that are in the container stays the same. But we can't always assume that. And so the combined gas law can be modified to include the number of moles of gas. And because what we know is this, is if we increase the number of moles of gas, then we're also going to increase the pressure. That means they're going to be directly proportional. And so the proper place to put this is we're going to put our number of moles of gas on the bottom. So it's this is sort of a modified combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. And so this is sort of our modified version. We won't really see this one very often, but you need to know it's out there. And this one lets us take account the number of moles. Now, with pressure, volume, number of moles, and temperature, these are the only four things which affect the behavior of an ideal gas. Nothing else does. If I want to change the pressure of an ideal gas, I can only change the volume and the number of moles of the gas and the temperature, and that's it. Nothing else makes a difference. If that's true, then if I have any set of pressure, volume, number of moles, temperature, that's going to equal that. So that's the before, right? So we've got our I've got sort of our before for this, and we've got our after for this. Now, what if we change it to another after? Well, we're going to get some other after, call it after 2, and then we could add some other after, call it after 3. It's always going to equal the same thing. All these things are equal. The before, the original before, and the after 1, and the after 2, and the after 3, they're always equal to some number. And so if they're always equal to some number, then that means we can say that for any possible set of conditions of pressure, volume, number of moles, and temperature, doesn't matter what they are, they're always equal to some number, which is going to be basically a constant. And so this constant here is going to be sort of what we're going to talk about here. So the two sides are equal for all possible factors, then both sides are going to equal constant. We're going to call this constant R. And so we could sort of rewrite this a little bit as P1V1 over N1T1 equals P2V2 over N2T2 is equal to this constant R. This constant R is called the gas constant. And so we'll see a little bit of this in a second. Sometimes it's also called the ideal gas constant. But this is our gas constant right here. And this is true for all gases, for all pressures, all volumes, all temperatures, that this P1V1 over N1T1 equals P2V2 over N2T2, or P a trillion V a trillion over N a trillion T a trillion is equal to R. This one number right here. So let's take a look at what we would do with that and how that becomes useful. If for any value of PV, N, and T, it's equal to the ideal gas constant, it's equal to this gas constant, we really don't need to worry about our numbers. Why not just say the pressure, the volume, the number of moles, the temperature? Get rid of our subscripts and just say, let's assume the gas isn't changing. Let's just assume we have a gas that has a pressure, a certain volume, a certain number of moles, and a certain temperature. If you do that, we can sort of rewrite this as being just PV over NT is equal to R. Now, we don't like having this division sign in the middle, so let's just go and take our NT and move it up to the top. And we do that, we end up with an equation that looks like this. PV equals nRT. This is the ideal gas law. Because this is true only for ideal gases, which we said most gases we run into act a lot like this. And so PV equals nRT. This is our second of our major gas laws. So we have the combined gas law that basically puts together Boyle's and Charles and Gay-Lussac's law all together. And now we have our ideal gas law that takes care of gases that basically aren't changing. Combined gas law deals with gases that change. We start with one gas, we change it to a gas that has different conditions. The ideal gas law lets us figure out that if we just know the pressure and volume and number of moles of a gas, we can find the temperature. No problem right there. Now, talk a little about R right here. So we said R is a constant, but we haven't said what it is. R is a gas constant. It's basically equal to 62.36 torr times liters divided by Kelvin moles. Okay? So R can be different for different units. And so if we were doing this in kilopascals rather than torr, then we would have a different value of R. If we were using, instead of liters, milliliters, we'd have a different value of R. But for the purposes of this class, we're going to go ahead and we're going to use 62.36. But because we're using 62.36 for R, that means that when we do this, our equation here, our ideal gas law here, the pressure is going to have to be in torr. It means the volume is going to have to be in liters. Number of moles as well, obviously just in moles, no problem there. The temperature, as before, has to be in Kelvin. And so basically what we've got here is, unlike the combined gas law, where you can use any unit of volume you want to, or any unit of pressure you want to, as long as it's the same on both sides, the ideal gas law requires that you use a certain set of units. And in this case, the certain set is torr and liters and Kelvin and moles. And so pressure has to be in torr, volume has to be in liters, temperature has to be in Kelvin, and moles obviously has to be in moles if you're going to use 62.36, which we will for this class. So let's try a little bit example-wise on this. So 0.076 moles of methane gas are collected at 35 degrees Celsius and 814 millimeters of mercury. So the question is, what is the volume of this gas? So to do this is that we say this gas is basically not changing from one thing to another. Since it's not changing, we're going to use the ideal gas law. And so PV equals nRT. And so do we know the original pressure of this gas? It says it's at 814 millimeters of mercury. Now, what we know is the pressure has to be in torr. So in this case, we're going to have to convert from millimeters of mercury to torr. Fortunately, that's easy because 1 millimeter of mercury is equal to 1 torr. So this is just going to be 814 torr. Got lucky on that one. Times the volume. Do we know the volume? It says, well, what is the volume? So we don't know that. So that's just V. Equals N. N is the number of moles, and it says here our number of moles is 0.76. Our unit is moles, as we said here, times R. And so let's look and see what is R. R, the gas constant, is 62.36. And so then for R, we'll put 62.36. And then lastly, times the temperature. The temperature has to be in Kelvin. We're told it's 35 degrees Celsius. And so then you'll basically go ahead and do it the same way we did before, is we want to convert this to Celsius. So we say 35 plus 273.15. And so we get 308.15. And so 308.15 Kelvin is our unit here. And so at this point, we've got everything. Just want to solve for V. So let's divide both sides by what's on the left here, 814, so that we get our volume by itself. And so we would say then multiply it out. So 0.76 times 62.36 times 308.15, then divided by the pressure, 814. And so when we do this, we get a volume of 17.9414. The unit here, we said, is going to have to be in liters. So we know it's liters right here. Significant figure-wise, taking a look at that, what we see is that we have 814, 3 significant figures. We have 0.762. 62.36 is basically is a conversion factor. It's a constant. And we said for the purpose of this class, anytime we're given a conversion factor or a constant, it's going to be considered to have infinite significant figures. And 308.15 is going to be, since we start off with 35 degrees C, it's rounded to the ones place. It's going to be around the ones place here, so it'll have three significant figures, 1, 2, 3, like that. And so our final answer is going to have two significant figures. So our final volume here is simply going to be 18 liters. And so that is how you use the ideal gas law. So let's try out another one. Let's see another example and see how that works. So in this example, we're told 15 grams of oxygen gas are generated by the decomposition of potassium chlorate. The gas is measured to occupy 1.2 liters at standard pressure. And the question is, what is the temperature of the gas? So in this case, the gas is not changing. So as a result, we're going to use our good old friend, the ideal gas law. And so to use the ideal gas law here, we'd say PV equals nRT, same as it has before. Do we know the original pressure? Well, let's see. It says 15 grams of oxygen gas are generated by the decomposition. The gas is measured to occupy 1.2 liters. That's standard pressure. Standard pressure here is, we'll have to find it the proper units. In this case, the units we need to use are torr, millimeters of mercury. And in torr, standard pressure is 760 millimeters of mercury, or 760 torr. And so times the volume. Do we know the volume of the gas? It says it occupies 1.2 liters. Okay, and it is in liters, so that's the right unit here. Equals N, the number of moles. Do we know how much oxygen gas we have? It says 15 grams of oxygen gas. So we don't have the number of moles, we do have the grams. But we can find moles from grams. So we're going to set up our table here. So we say 15 grams of oxygen gas, that's O2. And we want to get rid of grams of oxygen gas, and we want to go to moles of oxygen gas. And so in this case, how do we find the number of moles? Look at the periodic table. Oxygen is 16. There are two of them, so it makes 32 grams in 1 mole. And so in this case, you go ahead and we want to multiply across the top. So 15 times 1 divided by the bottom, 32. And so in doing this, we get a final answer of 0.46875 moles of O2. And so that's the number we're going to use for the number of moles here. So 0.46875. Note we don't round yet because we're not done with the problem. Times our ideal gas constant here. And so the gas constant, because of the fact that we're using torr and liters and all that, same one we always use in this class, 62.36. And so for R, you put in 62.36. And then lastly, times the temperature, which is what we don't know. And so that's what we're solving for. Similar to before, to solve for the temperature here, we're just going to have to divide by the two guys that are next to the temperature. So divide by 0.46875 and divide by 62.36. And we're going to say the same thing over here because I don't feel like writing it again. And so it cancels on this side, and we should be just left with the temperature. So we'd say 760 torr times 1.2 liters divided by our two guys that are going to be on bottom, which is 0.46875. And then 62.36, and we do that, I get a temperature of 31.19. And so we get an awfully, awfully cold temperature here. And so, because this has to be in Kelvin. And so 31.19 Kelvin. Significant figure-wise is, let's take a look at what we were given here. We had 760 torr, but it says standard, this is standard pressure. And so this is exact, so that has infinite significant figures. 1.2 liters has two significant figures. The number of moles here was based on our 15 here. Now, since that's spelled out, it means it's also going to be infinite. If it was just 5 grams, it would have two significant figures for this, so we just use 0.46 like those two. And 62.36 is also infinite. We've only got one thing that's going to determine this. That's going to be our number of liters, which has 2. So our temperature is going to have two significant figures, so our final temperature is 31 K. And so we have an awfully cold gas of oxygen here. And so that's our final answer. That's how you, once again, use the ideal gas law. So let's take a look at one last thing. Our one last note is this. How do you know which one to use, whether it's combined gas law or ideal gas law? Whenever you have a case where the gas is changing, where the pressure started off as one thing and now it's something different. The volume started off as one thing and now it's something different. You're going to use the combined gas law. So anytime the gas changes pressure, volume, or temperature, or some combination of those, you're going to use the combined gas law. You'll use the ideal gas law when either the gas is not changing, that is, it just tells you here's the temperature, here's the volume, here's the pressure, or something, or some combination of those, or you only know the pressure, volume, temperature, or number of moles for a gas at one particular time. And so you could have a case where basically you said you have a gas that starts off at 100 kPa and is compressed until it has a volume of 5 liters and it's at 200 kPa and so on and so forth like that, where you're given a lot of information about one state but not enough information about the other state. Then you'd still use the ideal gas law. So as a general rule, combined gas law for cases where the gas is changing, ideal gas law for cases where the gas is not changing. And so those are basically ideas on how you're going to know which gas law to use. But these are our two main gas laws we have here. So combined gas law, to some extent, goes beyond Boyle's and Charles's and Gay-Lussac's law because it sort of combines them all into one thing. And the ideal gas law lets us figure out what a gas is doing even when it's not changing.